Okay, now that we've gathered our data for Barbie, we're going to go ahead and look at correlation. So I have an example tedious task where you enter the digits 0, 1, 2, 9 and list 1. And then you time how long it takes you to enter 10 digits, 20 digits, 30 digits, 40 digits, etc. And so here's the 10. We did it up to 60 digits. And then these are the times we recorded when we did this activity, at least for one group. All right. So the reason I'm looking at this table, this is not something you're going to have to do normally in stats, is like do the x minus x bar and y minus y bar. But I'm going to show you a little bit about where correlation comes from. So we are going to take the x average, which is going to be 35 digits, and that makes sense because these are equally spaced. 35 will be in the middle. And we're also going to determine the standard deviation. I just did one var stats on this. And I'm going to subtract 35 from every one of these numbers. So 7 minus 35 is, whoa, I'm sorry, the x value, that's why. I'm going to do x minus x bar. So it's 10 minus 35 is negative 25. 20 minus 35 is negative 15. Now I'm going to repeat this for the y values because we have two variables here. And the average, when I add all these up, is 15.5 seconds after I divide by 6. And the spread here is 7.007 seconds. So the average spread, the average distance to the mean here for these values is 7. And the average distance to the mean here is 18 digits. All right, let's do the same thing here. We're going to go 7 minus 15.5 and continue on, and there are all our values. Now before, when we were doing standard deviation, we would square these and add them up, divide, kind of average them out, and then take the square root to get back to our units. This time what we're going to do is we are going to multiply these two values. So here are the products I get. And I would actually add these all up. And I'm going to show you how that comes into play into the formula for correlation. So the formula looks like this, and basically what we do is I would take all these values right here. So this is the products. I'd add them up, and then I divide by the standard deviation for x and y. So what this is like a kind of measuring the number of standard deviations away these things are from the average, okay? And then we normalize it. This is actually the number of degrees of freedom we have, n minus 2, because I need 2 points to start my line. So then graphing the data, we're going to say that, and when I put this on my TI-84, here's my scatter plot. What direction does this take? Remember, we got to do defs. Direction, unusual features, which we've already sort of talked about. Direction is positive. Unusual features, not really. Form, I'll get to in strength. All right, the question I have for you is the product of these two, what we had from our correlation formula, positive or negative? Well, we could go, if you look at the table you just recorded, were all those values positive or negative? Now, they can vary. Some can be positive and some can be negative in the same set of data. But in our case, they were all positive. And let's explain why. Here is where my average point is. So I'm going to kind of divide this up with this horizontal bar. So anything above this bar is above the y-average. Anything below this bar is below the y-average. Then I do a vertical bar. Everything to the right is above the x-average. Everything to the left is below the x-average. Well, what do you notice? It's positive. So when x is above average, so is y. So both of these are going to have positive differences. When x is below average, so is y. So I'm going to have two negative products, and I get positive. So for all these dots, now you could have had a dot over here or a dot over here, but the total sum would have definitely been positive because of this sort of positive direction. If I had switched it, what would have happened? Well, in this case, x would have been below average, but y would have been above average. That would be a negative product. And here, x would have been above average, but y would have been below average, also a negative product. So when the slope is positive, our correlation is positive. When the slope is negative, our correlation is negative. Now our form is linear, and the strength from what we can see looks quite strong. But we're going to tell you actually how to determine that numerically using this correlation that we calculate. So let's go over correlation again. So here's the formula again for correlation. What does that formula remind you of? In a way, it reminds me of variance, but it's standardized because we are dividing by the standard deviation length. So it's kind of like we're doing z-scores, almost variance of z-scores, and then normalized to n-2, which is the degrees of freedom, which we don't spend a lot of time discussing. But basically, degrees of freedom, you need 2 points to start a line, and every extra point you have gives you a degree of freedom. So when we're trying to do correlation, what we're trying to do is figure out which line would fit the best. Now, I'm actually showing you something called a residual. So if one thing I could do, let's say I had all these values and I wanted to predict what the average y value was. Well, I could just actually use the average y value, which is represented in this point right here. In fact, if I adjust this, you can see the average value changes. So this point represents the coordinates for the average x and the average y. But you're probably thinking, oh, you could do better than that, because if if x is high in this case, y is low, I should be predicting below the average value. If x is low in this case, y is high. So let's go ahead and do this. I'm going to adjust this line until I make these residuals hopefully as small as possible. This seems more like the line I would want. Now I do have a way of turning on the actual regression line, and I'm pretty darn close to it. And you can see that this is a very negative regression, all right? This is called the correlation, which is R, and it measures the strength of the correlation. In this case, if I were to put these points, let's go ahead and line them up all on a line the best we can. I'll just move them to my line that said move this. All right, so I'm just trying to put all my points on that line the best I can. Here I got -1. Now that doesn't mean that the slope is -1. What it means is that it's perfectly correlated, or almost perfectly, there we go, so that if I go down one certain way in x, then I go down the same way in y. That's, again, not to confuse it with the slope, because the slope here is -0.4. And that would say for every increase of 1 unit in x, I would go down -0.4 in y. What this correlation means is, think of it almost like a percentage, although it's not quite. It means that we are all our change is explained by this line. Now, can you have positive correlations? Sure. So let's go ahead and adjust these. And what is this biggest value of ours? Well, you'll notice I'm kind of messing with the dots now. And if I look at it, my R is getting very low. So how strong is this equation here, or this linear form? It's not very strong. In fact, if I make a nice little circle with the whole thing, like I just sort of have some dots around, it gets pretty darn close to 0. So the closer this is to 0, the weaker the strength. All right, now we're going to go ahead and make this a more of a positive correlation. So it doesn't matter which points you have where. And I'm going to try and make this perfect. So tell you what, I'm going to try and line up. Come on. I'm going to try and line up perfectly here. So this C is going to get on my line, and this A is going to get down on my line. And that's pretty close. Come on, B. There you are. All right. Oh, the strongest I could make this, and here, let me move the equation so you can see it, is a value of 1. So strongest correlations, and I'm going to go ahead and do this again with a steeper slope. So my slope is, not worried about that label, trying to get everything beautiful. And you can see that, again, I have a different slope this time, 0.72, and my correlation is still 1. So the correlation is just how well the x value predicts the y value. It is not the same as the slope. And we do have some ranges that we can use to determine the strength of the correlation. So we do have some guidelines. So this form and the strength for the largest possible value of R, well, R was 1. That was the biggest we could make it. And that was very linear with a strong positive association. When we had the most negative value of R of -1, it was still very linear, but there was a strong negative association. Is R the same as the slope? No, R just measures strength. Slope measures how much y changes with 1 unit change in x. And remember, when you're interpreting slope, I expect you to tell me how much whatever it is we're measuring for the response, the y variable, changes with every increase of 1 in the explanatory or x variable. So here we go. The possible values for the slope. We noticed when we had a negative slope, correlation was negative. When we had a positive correlation, our slope was positive. So the signs on correlation and slope should always match. The strength, the most strongest ones we were at -1 and 1. So this is one rough guideline. From -0.8 to -1 is considered strong. From 0.8 to 1 is considered strong as well. The weakest correlation we had was at 0, which was right here in the middle. And then again, we'll have these two are moderate, so they're in between the weak and the strong. Now, let's go ahead and match these images with the values of R. -0.928. That means we have a negative slope, and since it's very close to -1, it's a strong correlation. Which one of these looks the strongest? I would say that one right there. And it has a negative slope. This one is also a negative slope, and this is the only other one. So I know automatically it's this one. Notice how the correlation is in the weak area. It's between -0.5 and 0. So I would say that's the correlation for that graph. Then 0.002 would be very weak for linear. While there's a very strong association and pattern here, as far as doing a straight line, it's very weak. So we would say that's 0.002. And finally, that leaves us with 0.711, which is a positive, so we need a positive slope. And it's a moderately strong correlation. It's in between these two right here. So let's go ahead and look at one group who was late, and they gathered their own data for the Barbie bungee jump. So here are their values, all right? And I went ahead and entered the data here using a Staplet, which is a very easy to use applet. And the question is, how safe do we feel with Barbie's bungee jump if we would use this data? So let's go ahead and look at the graph that they did. Finishing entering the data. And then we're going to click Begin Analysis when it's done. So here we go. And you can see right below it, there's one thing called Calculate Correlation. So we can see that there's a very strong positive association between the number of rubber bands and the distance. And it shows because the correlation is 0.992. So this is positive and strong. Now, one of the group members snuck some extra rubber bands to collect some more data because he wanted to win the prize. And he added this point in. How does this affect our correlation? Well, basically what that means is that it follows along the line. So it's going to give us an even stronger line. And our correlation does actually go up. It goes up to 0.998. Then one group member also recorded data, except he accidentally left off a digit, and he said 6 rubber bands and 6 inches. Well, we know that doesn't make sense because it's shorter than the Barbie. So how does this affect the new correlation? Well, because it comes off the line, it makes it weaker. In fact, our correlation drops to 0.838. Still strong, even with this outlier, which would be an unusual feature. Now, the group had not followed directions. You probably noticed those measurements were different from yours, and that's because they did it in inches instead of centimeters. So what do we do here? Convert all these to centimeters. And I went ahead and used Staplet to get my new data, and we'll see what R is for that. Should it really change, though? Because all I'm doing is changing scale of distance. I'm not really increasing any distance, just the units of measure. And let's see what happens to the correlation. Takes a little longer to enter the decimals. And begin analysis, calculate correlation, and what do we get? 0.993, which is very similar. There's probably some rounding issues because we converted. Now, a few last things about correlation. And a very important thing that you understand is that correlation does not mean causation. So here's an example from TylerVingen.com of cheese consumption versus total revenue for a golf course. Actually, I think it's golf course revenue versus cheese consumption. Anyways, so if we graph these, look at this. What a beautiful correlation. It's the R is 0.9824. Do you think that increases in cheese consumption cause increases in golf revenue? No, that is another factor that may be causing a strong, there is another factor, a lurking variable that might be causing a strong correlation. And in fact, the lurking variable in our case is time. You could think that, okay, it's just over time things are growing. Maybe the economy's good, and you can see it's starting to take a dip. 2009 wasn't a good year. And 2001 was kind of slow because of, September 11th. So there can be other factors affecting both revenues, and it's not really cheese consumption causing golf revenue. So so both factors are increasing with time, and time is your lurking or confounding variable. So other facts and cautions about correlation. Both the explanatory and response variables must be quantitative. If you switch them, then the value for correlation will not change. Remember, in that formula, if you have the product of the differences in x times the product in differences in y. But if you have 3 times 4, is that the same as 4 times 3? Sure it is. So when you switch them, it doesn't really change things. Now, correlation R does not change also when you change units of measurement. When we change it from centimeters to inches, or I should say inches to centimeter, we pretty much got the same correlation. Now, correlation itself has no units of measurement. It is a standardized value. And correlation can only be used to describe linear relationships. We do not do regression for other forms. Later, maybe you might study that, but not today.